Gnanam paramam dheyam. Knowledge is supreme.
For the last few classes, we have been discussing vibration of polyatomic molecules, and we have discussed it using the concept of symmetry that we have developed. In fact, we will need to come back to symmetry once again for discussion of electronic spectroscopy, but today let us take a break from symmetry and let us discuss spectroscopy at least one day. Then next day onwards we will get back to symmetry once again. One thing I want to ask you, are we familiar with this LS coupling? Are you familiar with term symbols? Have you learned that in inorganic chemistry? No, I know you haven't. What about the majority? How many of us know term symbols? Okay. LS coupling, JJ coupling. Okay. So, we will see what we do about that. The problem is, once again, if I get too much into LS coupling and all, that will take time, but anyway, it is not as if we don't have time. Of course, the syllabus that we discussed at the beginning was too ambitious. We will not be able to discuss things like field effect. So, let us take it easy, we will see what one module today and starting now. Today what we will do is, we are going to do a brief introduction to electronic spectroscopy. So, what we do in electronic spectroscopy, of course, is that we have talked about rotational levels, we have talked about vibrational levels. Now, we start talking about electronic levels. Okay. And to start with, again, today's discussion will be largely on diatomic molecules, but it can be seamlessly integrated with the discussion of electronic spectroscopy of polyatomic molecules. But when we really want to discuss symmetry or the polyatomic molecules, you will require what is called the symmetry of states, right. So, that is something we will take up next day onwards. But before I go there, let me start with one question. What is an electronic state? What is it that defines an electronic state? Yeah, electronic states have specific energies, of course. We are talking about stationary states, but is there anything else that some molecular property that defines the state? Of course, stationary states have, but okay, anybody else? Quantum number? Okay. Okay, anything else? Something easy as usual? Sorry? Chemical bonding? Well, the answer I was looking for is electron configuration. See, electrons reside in different molecular orbitals, as you people have said correctly, right. Now, how many electrons are there in which molecular orbital? Each molecular orbital is associated with some particular energy. So, how many electrons are there in which molecular orbital, and what are the spins? Whenever you talk about more than one electron system, spins become important, as you have studied in the discussion of things like multi-electron atoms. So, an electronic state is defined by electron configuration and the spin of the electron, alright. But then when you look at electronic states, you cannot really neglect the vibrations and rotations either. This is important to understand. Why? Because if you think of an electron potential energy surface, this is the same diagram that we drew for our anharmonic oscillator, isn't it? It is just that when you talk about electronic states, you talk about not one Morse curve, but several Morse curves. The lowest one is the ground state, the higher ones are the electronic excited states. Each of these states is associated with vibrational levels, and each of these vibrational levels is associated with rotational levels. So, when I say that a molecule is in the ground state, ground electronic state, I also have to specify where is it. It will be in B equal to 0, that we know, but it can be in different J levels. Again, when we talk about a transition, transitions will originate here, I understand, but they can go here, they can take the system here. The moment transitions take place, you have to state what the destination is, not only the electronic state, but also the vibrational level, and if you have that much of accuracy, the rotational level as well. Alright. So, that is why we have to discuss vibration and rotation before we can talk about electronic spectroscopy. Now, our starting point here is going to be Born-Oppenheimer approximation. I think we have talked about this in this course earlier, have we or have we not? What does Born-Oppenheimer approximation say? So, suppose I want to write Born-Oppenheimer approximation in terms of wave functions, how do I write it? If psi is the wave function of the system, how do I express it? Psi, I will write Es, just to remind ourselves that spin is also important, E for electronic, S for spin, multiplied by, I will just write psi V, V for vibration, multiplied by psi R, R for rotation. Okay. So, and what about the energy? Total energy will be energy of, this time I will just write electronic, I can write Es plus EV plus ER, V for vibration, R for rotation. Okay. This is just a sum. Now, of course, let us not forget what is the magnitude of energies we are talking about. What is the typical energy associated with rotation? How many centimeter inverse? 10. 8 to 10 is making it a little too stringent. I would say 2 to 10 or something. 10 to the power 0 to 10 to the power 1. Okay. What is the typical energy associated with vibrational levels? Number, I am just looking for numbers. Just say you can either be right or you can be wrong. Nothing to worry. Rotation is 10 to the power 0 to 10 to the power 1 centimeter inverse. What do you think vibrational energy would be in centimeter inverse? Yes, not 4, I would say 10 to the power 2 to 10 to the power 3, right. So, think of the numbers that you see on a vibration spectrum, 1000 centimeter inverse, 300 centimeter inverse, 3000 centimeter inverse, 10 to the power 2, 10 to the power 3. What about electronic levels? What is the typical energy? Yeah, Vishwarup? 5, even 4. You can do a quick calculation. Electronic means what? UV is, right. So, say 400 nanometer is a typical, let us 300 nanometer, then it might be easier. No, why will it be easier? 400 nanometer. 400 nanometer, how many centimeter inverse is that? 400 nanometer is what kind of light? Red or blue or green or yellow? Okay, violet. They are being picky anyway. So, what is the centimeter, the wave number of that? Is 25,000. So, I said wave number. So, from when do we express wave number in nanometer? 400 nanometer is the wavelength. What is wave number? Yeah, it's 25,000, right? Why complicate things? 25,000, say 25,000. That's what we understand. Now tell me 10 to the power, how much is that? 2.5 into 10 to the power 4. So something like that, right? 10 to the power 4, 10 to the power 5. So when we are talking about something like a number like 25,000 or 18,000, 10,000, even 10,000. 10,000 is actually not even in visible range. Your instrument has to be really, really good if you also want to detect something like 2 centimeter inverse. So, generally it is enough if we consider these. For most of the discussion, we do not even talk about rotation. So, we write the wave function like this, we write the energy as sum of electronic energies and vibrational energy. Okay. Of course, you can see it if your instrument is good enough, that shows up as rotational fine structure in your spectrum. Once we are done with our discussion of electronic spectroscopy, we will quickly go back to rotation, and we are going to use this form of the wave function to talk about an aspect of rotational spectroscopy that we have neglected so far. Okay. The effect, in fact, because of this kind of wave function, nuclear spins also affect the nature of rotational spectrum. We will come back and talk about that as well, but in a couple of weeks maybe. For now, what we do is, for most of our work, we restrict to electronic and vibrational energies. Sometimes if we have an instrument that is good enough, then we talk about rotational fine structure. Maybe we will discuss that tomorrow, not tomorrow, next Monday. Okay. Now, before proceeding further with this, let us remind ourselves a little bit about spin. Okay. And this is how I like to do it. I do not know if I had done it in class already. Let us say I have a molecule, this is HOMO, this is LUMO. For most of the organic molecules, what you have is, you have 2 electrons in HOMO, right. So, I am going back to the question that I asked at the beginning of the discussion today, what is a state? Okay. How do we define a state in an easy manner? So, what is the electron configuration then? HOMO to LUMO 0, right. This defines a state, alright, and it is lowest energy state, ground state. What is that state called? I think we know this. That state has a name, right. It is a singlet ground state, right. We call it the S0 state. This is how we generally denote it. Okay. And the easy convention that we use is, we draw a picture like this and we say that this spin is plus half, this spin is minus half. So, total spin capital S is half minus half is 0. So, 2s plus 1 spin multiplicity is 2 into 0 plus 1, which is 1. So, it is singlet state. Now, when you do a HOMO to LUMO excitation, then what happens? You have 1 electron in HOMO, 1 electron in LUMO, HOMO 1, LUMO 1, that kind of a electron configuration. And in the easy convention, what we say is, we say there are 2 possibilities, the spins can be paired or the spins can be parallel. So, in this situation, what is capital S when the spins are paired? Capital S is 1, plus half minus half is 0, last time I checked, right. So, what you are saying is, spin multiplicity is 1, 2s plus 1 is 1. So, this is also a singlet state, but will its energy be more than or less than S0? Definitely more. So, it is a higher energy excited singlet state, and since it is the first state that you get upon excitation, you call it the S1 state, alright. Now, what about this? What is capital S for this one? Half plus half is 1, that is capital S, 2s plus 1 is 3. So, it is a triplet state, that is what we are used to thinking. And then is the energy same? See, in both the situations we have 1 electron in HOMO, 1 electron in LUMO, right. Are the energies same? Spin reversal is occurring in S1. So, spin reversal is taking place in T1. So, that will require extra energy. So, triplet has more energy, T1 has more energy than S1. So, Manthan says T1 has more energy than S1, but that depends also. Both possibilities are there. That is a safe answer, right. Now, he has decided to fence it, sit on the fence and says this is possible, that is also possible. Do you have somebody who can decide either this side or that side of the fence? I am saying always energy of S1 and T1 are different. So, no fence sitting on this at least. T1 will have greater energy. Does anybody want to say that T1 will have lower energy? Why? Why will T1 have lower energy? Highest multiplicity, so according to Hund's rule, right. But when, so we will accept this answer, but the actual answer is a little more complicated. But at least for now, it is fine if we say that according to Hund's rule. What does Hund's rule say? Everything else being the same, the state with the higher multiplicity has a lower energy. That is the way in which we have learned Hund's rule, bypassing all the mathematics. Okay. So, if you stick to that simplistic kind of thinking, T1 does have lower energy, alright. So, that is why generally you draw the energy manifold like this. I will just move it a little bit away, S0, S1, T1, something like this. But let us not forget something we have, all of us know already. Let us not forget that this picture is only approximate. The singlet and triplet really comes from a discussion of the spin wave functions of the 2 spin system, right. You have 2 spins, 2 electrons, each can have either alpha spin or beta spin. So, one situation is that both have alpha spin, alpha 1, beta 1, right? Alpha 1, alpha 2. 1 and 2 are identifiers of electrons, names of electrons, and alpha, beta, these are the spin wave functions. Alpha means the magnetic spin angular momentum is plus half, beta means it is minus half, up spin, down spin as we generally call them. So, both can have alpha spin, no problem. Can both have beta spin? Yeah, no problem. But as you have learned when you studied multi-electron atoms or molecules, the moment we go to the situation that one has alpha spin and one has beta spin, you cannot say that the wave function is alpha 1 beta 2 or alpha 2 beta 1, because electrons do not wear jerseys, right. This 1 and 2 are not written on the electrons, they are indistinguishable. So, all you can say is that one of the electrons has alpha spin, the other has beta spin, but you cannot say for sure that one has alpha, 2 has beta or the other way around. So, the situation is a linear combination of this and this, alpha 1 beta 2 plus minus beta 1 alpha 2, alright. And then as you know, if I write alpha 1 beta 2 plus beta 1 alpha 2, this is one possibility, and alpha 1 beta 2 minus beta 1 alpha 2, this is another possibility. So, as you can see, this alpha alpha, very commonly what we do is we drop, we do not even say 1 and 2, we say alpha alpha. The implicit meaning is first one is 1, second one is 2. Alpha 1 alpha 2, alpha alpha, beta beta, alpha beta plus beta alpha, all these are symmetric with respect to exchange. Okay. You can even say symmetric with respect to inversion. Alpha beta minus beta alpha is antisymmetric, right. If you interchange 1 and 2, then your wave function will change sign. So, if you remember Pauli principle, it taught us that the overall wave functions must be antisymmetric. In fact, when we talk about that rotational spectrum, this is what we will use later on. But for now, this is what it really means. We have 3 wave functions that are symmetric, they together make up the triplet manifold. Alpha beta minus beta alpha is a unique wave function which is antisymmetric, that is the singlet wave function. So, when we say singlet triplet, the implicit meaning is that singlet is actually only one wave function. Triplet is a combination of 3 wave functions. That is where it comes from. And also you can think that, okay, this means the spins are parallel, fine. Beta 1, beta 2 is also, that means spins are parallel. But alpha 1, beta 2 minus beta 1, alpha 2 means the spins are actually paired. So, you can also think that the triplet state really is only 67% spin parallel state, right. So, these arrows that we drew, they give us only an approximate picture. This is the real accurate picture. Okay. Please do not forget this. I am sure I have said this earlier, but this is something that I have seen we forget. This is so convenient and it is used all the time in photochemistry courses and it works for all practical purposes. So, more often than not we tend to forget this, but we will need it. In fact, somebody asked me once in class, is it possible to see the 3 triplet wave functions? What do you think? Do you think it is possible to see some signature of the 3 wave functions? We are saying that there are actually 3 wave functions which are degenerate. Okay. Is it possible to see? Do you know? It is possible to see. You apply a magnetic field, what happens is they interact differently. The moment you attract magnetic field, things which have different orientations of angular momentum, they separate out in energy. So, there are experiments in which you apply a weak magnetic field and you can split, not weak actually, you have to apply something like I think 1 Tesla magnetic field. And then not only can you see a signature of the 3 different wave functions, you can actually cause the system to shuttle between singlet and triplet states by application of magnetic field. So, they are actually there, it is not something we are making up from some weird unrealistic mathematics, fine. That is a point I wanted to make. Next, what did I want to say next? This is, we have defined what states are. Now, let us go a little bit into spectroscopy of these states. We will need the symmetries later on. I will just leave it here. So, as a first approximation, this is what we will deal with. And we talk about what kind of spectrum we can expect when you go from say singlet S0 to S1, or can you go from S0 to T1 and so on and so forth. Okay. These are the wave functions that we will use. Of course, in order to say whether we can have transition between 2 states, we need to talk about some kind of a selection rule. Before we go there, we will need something more, and that something more is Franck-Condon principle. Franck-Condon principle is something that I think everybody knows already. It is already depicted in this diagram. See, when I drew the arrows, I drew vertical arrows, didn't I? I did not draw an arrow like this. Franck-Condon principle essentially says that you cannot draw a bent arrow. What does that mean? When you draw a vertical arrow, what is x axis? If it is a diatomic molecule, it is very easy to understand. X axis is internuclear distance. So, if you draw a vertical arrow, what do you mean? That means energy is going up, but internuclear distance does not change. That is essentially what Franck-Condon principle states, that since nuclei are much heavier particles than electrons, during the motion of electron, you do not need to consider the motion of this big fat nuclei, they are too sluggish. In fact, that is something that comes from your Born-Oppenheimer approximation as well. So, that is why we always draw vertical arrows. Now, with that understanding, let us see what kind of selection rules we are going to have. Okay. These are the wave functions, and you have your dipole moment. So, you have to write the transition moment integral. Alright. This part, the discussion we had so far, I think is there in any standard textbook, even Atkins Physical Chemistry or Van Wil's Spectroscopy, everywhere. What we are going to discuss now is there in Harris and Bertolucci's book. We have not really used that book too much so far, now we will. Harris, Harris and Bertolucci. So, this discussion now is from Harris and Bertolucci's book. What will the transition moment integral be? one thing we should not forget is that we have two kinds of coordinates now, because you have nucleus and you have electron, right. When you talk about vibration, vibration is associated with movement of what? Nucleus or electron, nuclei with respect to each other, right. So, what we will do is we will write the, and when you have a vector dipole moment, of course, you can write it in terms of nuclear as well as electronic coordinates, you need both, one is not enough, is not it? Displacement of nuclei, displacement of electron, both are required. So, we will write mu as mu n plus mu e, nuclear and electronic component, and transition moment integral will become, suppose I say that this first state is 1, second state is 2, this kind of a transition is what I am talking about. It will be what, how do I write it? Psi 1 es, why am I writing 1 es? Psi es 2 psi v 2 mu n plus mu e psi es 1 psi v 1. Are we okay with this form of transition moment integral? This is the wave function of the origin, this is the wave function of the destination. Instead of writing L and M once again, I am just writing 1 from for the level from which the transition begins, 2 for the level at which the transition terminates, okay. And I have neglected psi r for now, we will just consider vibrational levels. Of course, you break it down. Achha, what is d tau? It is when you write like this, sometimes you forget what d tau is. Volume element. Volume element will also comprise of a nuclear term and electronic term, right? Right or wrong? What was the volume element in say Cartesian coordinates? dV equal to or d tau equal to dx dy dz. What was it in terms of spherical polar coordinates? R squared dr sin theta d theta d phi. So, that is what I am trying to say. When you have two coordinates 1 and 2, d tau is essentially d tau 1 d tau 2. So, let us not forget that I am not writing it explicitly, but it is there. So, in fact, if you read Harrison Bertolucci's book, they have not used this bracket notation, but Harrison Bertolucci is a printed book. So, if you see that they have actually used explicitly d tau n and d tau es. Do not forget d tau is a product of d tau n and d tau es. Okay. So, let me write like this: integral psi es 2 psi v 2 mu n psi es 1 psi v 1 integrated over all space plus integral psi es 2 psi v 2 mu e psi es 1 psi v 1. Alright. Now, if you look at the first integral, I can write it as a product of two integrals, one in nuclear coordinates, one in this electronic coordinate. What will be the factors in the integral in electronic coordinates? Psi es 2, psi es 1 integrated over all d tau es, and that will be multiplied by psi v 2 mu n psi v 1. Are we clear? Maybe I do not need this anymore. Right here, TMI is equal to, first term is psi es 2 psi es 1 integrated over all space. When I say space, I mean electronic space, and multiplied by psi v 2 mu n psi v 1 integrated over all space in nuclear coordinates. First term is taken care of. Are we clear about the first term? Any question? Second term plus, what will the second term be? This time this, so this time what will it be? It will be psi es2 multiplied by mu e multiplied by psi es1 integrated over all space in electronic coordinate, that will be one integral, that will be multiplied by integral psi v2 psi v1 over all space. Okay. So, I will write that psi v2 psi v1 integrated over all space multiplied by psi es2 mu e psi es1. Okay, these are the two terms we have. Now, look at the first term, integral of a product of two electronic wave functions, two different electronic wave functions of the same molecule. What will that be? That will be 0, because they form, they are member, yeah, yes, they form an orthonormal set, and that is why it is 0. So, good thing is this first term becomes 0. Okay, we agree that this is equal to 0. Why? Because these two are members of an orthonormal set, two different members of orthonormal set, right. So, in the TMI you are left only with the second term. Now, tell me, similarly, if these two, if this integral is also equal to 0, then TMI is always equal to 0 and we can go home. We can have an early lunch today and there will be no electronic spectroscopy in the world. So, obviously, this is not 0. Can you tell me why this integral is not 0? Integral psi v2 psi v1 over all space, why is that not 0? Different states, okay, but they are of different electronic states, right. So, they belong to different vibrational manifolds. Do not forget that this psi v1 is here, psi v2 is here, right. So, this is one orthonormal set, that is another orthonormal set. A wave function from here and a wave function from here are not orthogonal to each other, right. My 1s orbital and your 1s orbital are not orthogonal to each other, okay, that is what it is. So, the second term, thank God it survives, otherwise there would be no electronic spectroscopy. So, transition moment integral then would be equal to, I will write this psi v2 psi v1, and I will expand this a little bit. Before that, let me tell you what this is called. Does anybody know what this is called? What is this called? It is called the Franck-Condon factor. It is called the Franck-Condon factor. So, let us take an example. Let us say the situation is like this, and I think many of you might be actually familiar with what I am drawing now. The two energy minima can be connected by the same vertical line. What does that mean? Equilibrium bond lengths are same in ground and excited state. In that case, what will happen? Of course, all upward transition will begin at v equal to 0. So, this is your wave function, this is your psi v1. In this case, think of psi v1 and think of psi v2. What does this integral mean? This integral means I should take this psi v1, if I try to plot psi v2 on top of this, I hope you will agree with me that there will be a more or less complete overlap, right. This integral means you multiply this by this and find out the area, right, agreed or not, okay. This is something like what we have learned in bonding. In bonding we talked about overlap integral. What was overlap integral? You have 1s orbital of atom A you have another 1s orbital of atom B, the overlap integral is integral phi a phi b over all space, right. Why is it called overlap integral? Because this integral has a non-zero value only in areas where the two wave functions have overlapped, because it is a product. This is the same thing, but with vibrational wave functions, right. So, what it means is that if there is a good overlap, then this Frank-Condon factor will be large. Now, you think if there is a little bit of displacement, this is your 0th vibrational wave function of the lower electronic level. Let us say the equilibrium bond length is a little more. What will happen? Now, the overlap is this, less than what it was earlier. So, if the equilibrium bond lengths are not same in ground and excited state, then what happens is that the Frank-Condon factor for the 0 dash transition or 0 double dash transition, whatever you want to call it, that becomes smaller and smaller. Okay. What effect would that have on it? This is what is multiplied by the second integral, right. So, a larger Frank-Condon factor would mean a larger transition moment integral, and by now you know very well what is the meaning of a larger transition moment integral. How is transition moment integral related to probability of transition? Square, right. So, larger transition moment integral means a larger probability of transition. How is a larger probability of transition manifested in the spectrum? Greater intensity of the spectral line. So, intensity is determined by the Frank-Condon factor. Next, please read the discussion in Manuel's book about what spectra look like, which line is most intense when the equilibrium bond length goes from being the same in ground and excited state to being the equilibrium bond length being longer in the excited state to equilibrium bond length being shorter in the excited state. Okay. Those pictures are drawn very nicely in your Manuel's book. You can read them from there, absolutely descriptive. Just do not forget that the reason there is the change in Frank-Condon factor. Let me write the second part, second factor now, and while doing it, let me do a little bit of expansion. Yes. Sorry. So, if the equilibrium bond length is different, what will happen? Let us say this is V equal to 0 wave function, right, and this is a V equal to 0 wave function of the excited state. If equilibrium bond length is same in both the cases, then you have an exact overlap, right, like your total eclipse, that kind of a thing. So, you can understand Frank-Condon overlap will be maximum. Now, if the equilibrium bond length is a little more, what will happen? The overlap will be like this. So, it will be the area will be much smaller, and in that situation what is likely to happen is that now think of V equal to 1. Initially what happened, this is V equal to 0, V equal to 1 is something that I cannot do with my hand because I do not have enough joints, it is a complete sine wave, right. So, what was happening then was that the sine wave had a minimum in the middle, okay, and then this was minus. So, overlap would be 0 actually. Now, if that moves a little bit, then it might move sufficiently so that the half of the sine wave comes exactly here. Then the transition between 0 and 1 dashed, 0th vibrational level of ground electronic state and V equal to 1 of the excited electronic state, that might have the greatest Frank-Condon factor. That is what I am trying to say. Are we clear? Now, yeah. Oh, so for that what you need to do is you will have to write the form of the wave function explicitly. So, you know the form of the wave function anyway, right. So, the only difference is that you write the vibrational wave function in terms of x. What will x be here? This and that will be related by this. If I call this x1 and x2, they will be related by the difference in equilibrium bond length. That is how it will show up mathematically. Okay. Now, how can I expand this? I have written psi EF, which means that that is the wave function for the electronic state, which includes the spatial part, the orbital part and the spin part. As a first approximation, they should be separable. So, I should be able to write something like psi Es is equal to psi E into psi S. Okay. When this happens, we say there is no spin orbit coupling. Okay. So, this then becomes integral psi Es, sorry, psi E2 mu E psi E1 integrated over all space. Now, I will need this part multiplied by psi S2 psi S1. Are we clear? No spin orbit coupling. So, I should be able to write this integral as a product of two integrals, one in electronic coordinates, one in spin coordinates. Okay. When I do that, this is what I get. So, now see, when will transition moment integral be non-zero? Of course, your Frank-Condon factor will always be non-zero. Okay. Whether it is large or whether it is small, determine whether the transition is strong or not. What about this? Will it always be non-zero? No. How do we know whether it is non-zero or not? From symmetry. That is why we will have to go back to our discussion of symmetry. What about this? This is in spin coordinate. Spin coordinate is a funny customer, as we know, right? When is this 0? When is this non-zero? When spins are same, then it is non-zero. When spins are different, then 0. So, one example, of course, when I say spins are same, spins are different, what do I mean? If you take alpha 1 alpha 2 and alpha 1 beta 2 minus beta 1 alpha 2, please work it out. This particular problem I think is worked out in Harrison-Bertolucci's book. So, I encourage you to work out that integral using all possible combinations. What are the possible combinations? One is singlet singlet, that will be non-zero, you will see. Second is you can do singlet with each of the triplets, they will always be 0, alright. Next you can of course do each with itself is trivial. Now you can see that if the initial spin function is alpha 1 alpha 2, final spin function is alpha 1 alpha 2, it will be non-zero. I encourage you to try out and you can see it again, you do not even have to do it. What happens if there is a transition between alpha 1 alpha 2 to beta 1 beta 2, is that possible? Alpha 1 alpha 2 to beta 1 beta 2, what will the integral be? Integral will be integral alpha 1 alpha 2 beta 1 beta 2 over all space. Now, this is in terms of coordinates of 1 and coordinates of 2. So, it will be product of integral alpha 1 beta 1 over all space and integral alpha 2 beta 2 over all space, that is 0. So, what we know already is delta S must be equal to 0. What we also need to remember is delta Ms also has to be equal to 0. I am not doing it here because in any case when we talk about NMR spectroscopy, we are going to deal with the spin wave functions. But please go through Harrison-Bertolucci's book and satisfy yourself and work it out yourself. It is very simple algebra. Satisfy yourself that this is the condition. So, if this part of the transition moment integral is 0, then the transition is spin forbidden. If this part is 0, then it is orbitally forbidden. Okay? And generally what happens is there are ways by which you can beat these forbiddenness. As we will see using arguments from symmetry, an orbitally forbidden transition can be vibronically allowed. Vibronically allowed means you do not have to always go from 0 to 0, right? V equal to 0 to V equal to 0, not necessary. You can go from V equal to 0 to V equal to 1. The moment you do that, symmetry of V equal to 1 will come into play and something that was not allowed will become allowed. We will study it next week. Okay? So, Orbitally forbidden transitions sometimes are rendered allowedness vibronically, but it is not so easy to render some allowedness to spin forbidden transitions. What is the mechanism by which spin forbidden transitions can become allowed to some extent? I think you know this, most of you. It is called spin orbit coupling. Due to spin orbit coupling, the nature of the spin can get modified. We will discuss that briefly also. So, this is the expression for transition moment integral. If this is 0, then it is orbitally forbidden, it can become vibronically allowed. So, typical epsilon values for orbitally forbidden, but vibronically allowed transitions would be something like 10 to the power 1 to 10 to the power 3. If it is spin forbidden, typically values would be 10 to the power minus 3 to maybe 10 to the power 1. And if this is non-zero, this is also non-zero, then you have really high epsilons. That is the case in these dye molecules that you use, right, brightly colored stuff. For them, the epsilon values are 10 to the power 3 to 10 to the power 5. In some cases, it can be even 10 to the power 6. Okay. So, that is the definition of a fully allowed transition. Fully allowed transition means both these integrals are non-zero. Orbitally forbidden transition means this is 0. Spin forbidden transition means this is 0. Okay. That is the terminology. We have introduced that. We are going to make use of this next day, and let us see how far we can do. Before talking about symmetry of states, we will try to provide a brief discussion of LS coupling. So, that is what we are going to do next week.